Hello everyone, today I'm making a new movie in order to continue our chapter 6. We already watched and learned 2 movies already, and this is the 3rd movie that we continue our content from for chapter 6. Okay, this is the last slide of movie 2. And I also asked you to practice share review and to do homework for this page. Okay, this is new point: binomial probability distribution. Binomial, by that means two terms, two faces, or two events, or two things. Okay, so binomial probability distribution. What does it mean, binomial probability distribution? Binomial probability distribution is a special discrete probability distribution that has these characteristics. So binomial probability distribution is a special discrete probability distribution that has these characteristics. 1. An outcome on each trial or test of an experiment is classified into one of 2 mutually exclusive categories. One of 2. Okay, so this probability has only 2 possible outcomes. That's why we call binomial. That's why the probability that has only 2 possible outcomes. Okay, that's why we call binomial. That means a binomial is 2 possible outcomes. So this means that probability that has only 2 possible outcomes. For example, among in the class, if I select one student that I selected could be male or could be female. That's why only male or female. No the other third outcome coming. So okay, this is binomial probabilities. So the first an outcome on each trial or each test of an experiment is classified into one of 2 mutually exclusive categories. For example, a success or a failure. That's why when we do one test, or when we conduct one trial, or when we conduct one experiment, the possible outcome is only 2. Male or female, success or failure, pass or fail. But in this case, we just assign success or failure. Success outcome refer to outcome that we want to see. Failure outcome refer to outcome that you don't want to see. Okay, this is the first characteristic. Second one, the random variable counts the number of successes in a fixed number of trials. Okay, so we have the fixed number of assumption. It has a fixed number of an experiment. Okay, and random variable counts the number of success because we are interested to see the success outcome. The success outcome refer to the outcome that we want to see, that we want to get. Okay, so second one, the random variable counts the number of successes in a fixed number of trials. The third one, the third characteristic, the probability of a success stays the same for each trial. So from one test to the other, from one trial to the other trial, the probability of success is the same. Okay, is the same. So does the probability of failure. That means probability of success stays the same from each trial, or from one trial to the other trial. And probability of failure also stay the same from one trial to the the next. Okay, but normally failure we are not interested to see. We are interested to see the success. The trials are independent. That means the first test and the second test not depend on each other. Okay, the first trial or the second trials are not depend on each other. The trials are independent, meaning that the outcome of the first trial and outcome of the first trial does not affect to the outcome of second trial or the other trials. It means that the sampling is done by replacement. So the sample that we select from population is done by replacement. Okay, so that means we select and then we take it into the sample again before we doing the other test or the other trial. To compute a particular binomial probability distribution, we need to use, okay, n. What is n? The number of trials, the number of tests in our experiment. 2. The probability of success outcome on each trial, that we call pi. Pi is probability of success on each trial. Okay. So binomial probability distribution is computed by this formula. Okay, when you see this formula, it's hard to remember. Sure, I also agree with this one. It's hard to remember, but it will be less harder, become more easier to remember when you have more practice. Because the more practice, the more remember this formula. Okay, but however, I just distinguish, or I just explain this formula. So this formula, binomial probability distribution, Px, probabilities of x is success outcome, this formula come from 3 parts: the first part, second part, and the third part. Okay, binomial probability distribution, Px, x is success outcome. So probability of success outcome equal to 3 parts multiply each other. The first part is about combination of the total trials. Among the total trials, the success outcome. Okay, the combination among the total trials, and we get success outcome. To see success outcome, this is combination among total trials, success outcome. We can get combination from the combination of success outcome among total trials or number of trials. This is the first part is about combination. Second part is about probability. Probability of success, exponent or raised to x. Exponent x or raised to x power. That's why this probability of success, x also success. Okay, so multiplied by probability of success raised to x power. And the third one, probabilities of failure, because 1 is 100% or probability. That's why when we take 1 minus success, when we take 1 minus of probability of success, this is probability of failure. Multiplied by probability of failure raised to x n minus x exponent of power, raised to n minus x power. Okay, so this is probabilities of failure. This is the outcome of failure, because this is total outcome, total trial, and this is outcome success. That's why when we take a total trial or total outcome minus total success, this should be the failure outcome. Okay, so again, binomial probability distribution Px, P probability, X is probability of outcome, success outcome. So probability of success outcome now could be 3 parts multiplied to each other. The first part is combination of success outcome among n total or number of trials outcome. Okay, success outcome among number of trials. Second part multiplied by second part. Second part is pi probability success. X is success outcome. That's why pi raised to x power. Pi raised to x power means pi is success, probability of success, x is outcome success or success outcome. And then the third one multiplied by failure. So because of pi probability success, 1 minus probability success is probability of failure. The probability of failure raised to event or outcome of failure power. Okay, so 1 minus probability success, this is probability of failure. N is total trial minus outcome of success. That's why this is outcome of failure. Okay, so binomial probability split into 2 parts, but we multiply each other by taking combination probability success and probabilities of failure. Okay, we are C combination and total of trials. X is number of success or maybe number of success outcomes. Pi is probability of a success. Okay, a success on each trial. That's why we can find Px here. Okay, so this is combination formula. So I put here because I'm afraid that some of you already forgot from previous chapter. For example, okay, in order to make more clear understanding, we will look at example. There are 5 flights daily every day. There are 5 flights daily from Phnom Penh to Singapore. Okay, there are 5 flights every day from Phnom Penh to Singapore. Suppose the probability that any flight arrives late airport is 0.20 or 20%. Suppose that any flight arrives late, flight 1 arrives late, or flight 2 or flight 3 or flight 4 or flight 5, but not all fly together, only any one. Okay, only any one. Suppose the probability that any flight arrives late is 20% or 0.20. Question: what is the probability that none of the flights are late today? Okay, today. So this is experience, not today. Suppose that any flight probabilities or any flights arrive late, 20%. This is maybe based on previous maybe in the past days. But now we're asking, what is the probability that none of the flights are late today? No one late. What is the probability that exact one of the flights is late today? What is the probability that exact 2 of the flights are late today? Not are late. Okay, it should be are late. What is probability that exact 2 of the flights are late today? Exact 3 of the flights are late today, exact 4 of the flights are late today, or exact 5 of the flights are late today. Okay, so this is we use binomial probability distribution because flight is only arrive on time or arrive late. Okay, arrive on time or arrive late. That's why only 2 outcomes. So earlier we don't earlier on time we classify into only 1 outcome. But we in this case we are interested to see only arrive late because arrive late may be the problem. Okay, so we have that n equal to 5 because 5 flights every day. Pi is 20%. Probability a particular flight is late is x. X stands for the probability, or x stands for is the number of flight lates. Okay, x is stand for the number of flight late today. Pi equal to 20 is probabilities of any flight late, any flight is late from maybe from experience. Okay, because there is no flight late, x equal to 0. That's why p0 equal to combination 0 among 5 multiplied by probabilities of late raised to 0 power multiplied by non-late probabilities of non-late raised to the number of non-late. So there's no late, that's why all are non-late. That's why you can see this is a combination. This is yes, you can use a calculator. You can go calculator. So we got this one. Okay, probability that non-flight is late, non-flight late today is 0.3277 or 32%, 32.77% or about 33%. 2. What if probability that exactly 1 flight is late today? Because only 1 flight is late and x equal to 1. That's why p1. This is a combination among 1 of a combination of 1 among 1 flight among 5 flights. Probabilities of flight late raised to 1 flight late. Probabilities of non-flight late raised to number of flight non-late, no late. That's why we got this one. About 41% or 0.4096. Okay, so probability the exact 1 flight late is 0.4096 or 41%. It's about 41%. Okay, so when we calculate all answer here, you can see this table. This table called binomial probability distribution. This is probability distribution. This is probability distribution, but because of this probability from event that we conducted, the event that we conducted or that we do has only 2 possible outcomes. That's why this is we call binomial probability distribution. Okay, success outcome refer to the outcome that we are interested to see, to study. Okay, that's why this is binomial probability distribution. This is a possible outcome. This is together with probability of each outcome. All probability together equal to 1. Okay, if we take this one, take a table to draw a bar chart. Okay, to draw a bar chart, we got this one. That's why based on bar chart, we can see that the probabilities exact 1 flight late today is bigger, about 41%. Okay, probabilities are all flight late almost 0. Okay, probabilities of non-flight late is about 36. Oh no, it's 30. This is 35, maybe 33. Which one? 33, yes, 33%. So probabilities are all flight are late is about 0%. Okay, this is about 0%. This is binomial probability distribution. This is a bar chart that we use this table to convert into bar chart. A binomial probability table is a table that shows us the quick way of determine a binomial probability distribution. Okay, so you can go to appendix of your textbook, especially based on this example. You can go to page 774. You can see appendix 9. Appendix 9 is about table of binomial probability distribution that will show you number of trials and number of success outcome with probabilities of success outcome. Okay, so this number of trials, this is number of success outcome that we want to study, want to see. These are the probabilities of success outcome, but not now. This should be from the past. This is now what we want to see. Okay, based on our example earlier, you can see how many, this is percentage, this is percentage. This is table that we see. Okay, this is table we see is about this is round up. It should be 32.77, but it just rounded up to 7 to 8, 32.8. Okay, this is what our answer. Sometimes you don't need to calculate, but you don't need to calculate as I presented you previous slide. If you know n, if you know x, and you know pi, you can see example from this appendix. Okay, you can see from appendix, but this appendix in terms of probability is very limited. N can be yes, more than, but however n cannot be, we don't have a table up to n equal to 100. This is too long tables. That's why they don't provide you n equal to 100 or x equal to maybe 90 something. So this is cannot be because too long table. We can use appendix in order to see the result by not calculating using the formula. Only a special case. You see, special case. This is 5%, 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90%, 95%. So you can see any tables, the pi probability success is only very limited amount. It's only a very limited amount, only 5%, 10%. How about pi equal to 0.13? Can you see this one? No, we cannot see. If pi equal to 0.13, not 10 or not 20, you need to use formula as I presented previous slide calculation. You cannot see result, or you can see answer based on this table. This table is only very special pi. You see, only special pi. If pi number probability of success may be 24, you cannot find 24. It's only 20, 30, no 24. Okay, 0.24 for example. You cannot find. That's why you need to use calculation based on formula. Okay, so, but if you know that n is low, is less, x is so less, and pi is very good, pi is probabilities of success very good number, like this one, you don't need to calculate. You just go to the table, appendix table, you can see the result. Okay, but however pi is not special like this one, you need to calculate based on previous slide. Yes, this is calculate like this one. Okay, Study example and set review 6.3 on page 198, page 199. Okay, don't forget to do these ones. Appendix B on this page, previous one that I showing us the combination probability table is somewhere limited. Maybe I also explained somewhere is limited because especially probability of success is only very limited. Okay, pi is only very limited. Pi is very limited. 0.05, 0.10, 0.20, 30, 0.40, 0.50, 0.60, 0.70, 0.80, 0.90, 0.95. This is very limited. Okay, I also explain this one. This is because this table shows us the limited number of n's and probabilities. However, if we don't have a limited or we don't have special case like in the table that I presented previous slide, we have the other two methods for computing binomial probability distribution, all cases beside formula that I show in slide 24. Okay, beside this formula, we still use table I show appendix, but somehow the table appendix is very limited. So in order to compute all cases, we can use 3 formulas, including this one and these 2. One previous one on slide number 24 that I presented you, and we also have the other 2 methods in order to compute binomial probability distribution for all cases. 1. Normal approximation. 2. Binomial. Maybe we used, you can see chapter 7 on this page, but we have no time to go there. 2. We use computer, Excel especially, Microsoft Excel. So if we have a special case, we can see table appendix, but we don't have special case. For all cases, we can use 3 formulas. One I presented you in slide number 24 and the other 2 in chapter 7, but we don't have time. You can go to see by your own. And we also have computer. If you have computer, you can use Microsoft Excel to compute binomial probability distribution. Okay, this one. If you go to Excel file, insert function and binomial probability, you can see this one. Okay, this is number of what? Yes, this is number of success. This is number of trials. This is probability of success. And cumulative just put fall, and then you can get formula. Okay, this is x, this is n, this is pi. This is just put false, and then you can see the result. Verify this result with the table on slide number 39. 6. Okay, this 6. Slide number 39. Maybe we don't have this one. Slide number 39. We don't have. Sorry, this is we don't have slide number 39. But you can go to appendix. On page. We don't have slide number 39. Okay, maybe I delete this one. But we can go to appendix. This is appendix. This is n equal to 5, but in our this one n is not equal to 5. N equal to 6. That's why we go to 6. This is n equal to 5 on page appendix 6. Appendix B on page 774. But you go to 6, page 175. You can see x is 3, n is 6, 40. x is 3, n is 6, and 40 is 40, this one, okay, you can see this one, and 6, x 3, and pi 40, okay, same, yes, same, 0.2765, I think, yeah, okay, they round it up. You round it up, 2765, but they got 6 because they got only 3 digits beyond a point. Okay, this is a binomial probability distribution, different shape. Different shape. First, we will look in the shape, the appearance of the distribution. Vary, pi change, but n not change. Number of trials not change, but probability success change. Okay, number of trial 10, 10, 10, 10, n equal to 10, but probability success first only 5%, 0.05, 0.10, 10%, 0.20, 20%, 0.30, 0.50, 50%, 0.70, 70%. You can see first more outcome tend to be less number, less success. The less success tend to be more probability, but then change. Okay, I just so tend to be like this one, the distribution, and then the change like this one, and then okay, and then like this one, and then like this one, and next change. Okay, you can see the change little bit by little bit. So when we have n constant and we have probability of success change from smaller to larger, the outcome tend to be change. The first, when pi is smaller, the more outcome tend to go to probability success with the less amount, with less. But when pi come later, it tend to be more distribution. This is tend to be what to be skewed to the right, because this is tail, this is head. This is a head of animals. Remember that one? This is tail. But this one tend to be symmetric. Okay, but if you continue bigger, it should be like this one. Okay, it should be this one. So left, skewed to the left, negative skewed. Okay, this is based on distribution. Graphing probability binomial probability distribution for pi of 0.05, 0.10, 0.20, 0.50, 0.70, while n is constant. So we got this one. However, this one, when n is not constant, n is changed, but pi is constant. Probability success constant, but number of trial changeable. So you can see it's similar though. This is number of success. Okay, because probability is constant. Let's say 40. No, 10. But first we just do 7 trials, and then 12 trials, 20 and 40 and up to on. You can see compared to previous slide, it's similar distribution. Okay, similar distribution. But if you can more, this is become distribution like this is almost bell shape. This is almost symmetric, but not yet symmetric. Maybe we can go to the other one, 50 or 60. We can get this bell shape or symmetric distribution. Okay, so this is probability distribution, the shape or the appearance based on the graph that we draw. So it's similar to each other between the previous slide. Previous slide is about n is fixed, but pi is changing, but now n is changing, pi is fixed. Okay. Mean stand for MUI stand for mean of binomial probability distribution. Variance stands for sigma square of binomial probability distribution can be computed by mean of binomial probability distribution can be here. Okay, and probabilities number of trials pi probability of success. So why when you take number of trials multiplied by probability success, this is mean of binomial probability distribution. Variance. In order to get variance, sigma square equal to number of trials multiplied by probability success and multiplied by probabilities of non-success. Non-success, that means failure. Okay. So n number of trials multiplied by probability of success. This is MUI. Variance, number of trials multiplied by probability success multiplied by probabilities of failure. This is variance. So when we take the square root, this is standard deviation. Okay, let's take square root. This is standard deviation. Okay, go back to our previous example. There are 5 flights daily from Phnom Penh to Singapore with probabilities any flight late 20%. What is the average number of flight lates today? What is the variance of number of late flights today? What is the standard deviation of numbers of late flights today? Okay, that's why this one. So mean, in order to find mean of binomial probability distribution, you take number of trial multiplied by probability success, 1 flight late. In average, today we have 5 flights. Today, in average, 1 flight is late. Okay, standard deviation is about 0.90 or 9. That's 90. It's almost 1. Okay, it's almost 1. But actually, we don't have 0.90 flights. Flight cannot be 0. something. Cannot be 1 point something. It's only 1, 2, 3, 4, 5 flights. But we cannot up to 1. Okay, up to 1. That means in average 1 flight is late today. If we calculate it, but could be 0 flight late. This is 1 flight late. Exact average 1 flight late, but sometimes less than 1 flight late. It should be 0.11. So this is 1.89. So 0.11 should be 0 flight. 189 should be 2 flights. So in average today 1 flight late, but sometimes it's changeable. It should be from in average from 0 flight to 2 flight will be late. Okay, in average only 0 to 2 flight will be late. So okay, 1 flight less 0.89 flight less than average late, 0.89 flight more than average will late. That's why any flight will late is about 0 and 2 up to 2 flight late. This is when we calculate in terms of average. But actually, any flight could be late actually. But this is in terms of calculated in terms of average or maybe central tendency and variance from 0 to 2. Not 0, 0.11 to 1.89. But flights, we don't have 0 point something or 1 point something. That's why we round up. This is round down, this is round up. Okay. Okay, this is your homework. Do exercise as a homework on page 201 and 202. 201. Okay, no, that one. Also 201. This is 201. Number 10, number 12, number 14, number 16, number 18. Okay. This is your homework. This week is the last homework. number 10, number 12, number 14, number 16, number 18. Okay, I promise that this is the last homework for your course term. Okay, this is cumulative. Now before we look at binomial probability distribution, but now we will study cumulative binomial probability distribution. What does mean cumulative? Cumulative means additive. Actually, we already learned from chapter 3 how to find median from group data. Remember that? Remember this one? How to find median from group data. That's why in order to find median from group data, you need to find CF at that time, right? What does it mean CF? Cumulative frequency at that time. So I hope that you still remember that one. Okay, but now cumulative, additive. Cumulative probability distribution, that means we add one probability to the other one additive. For example, a study by Department of Transportation concluded that 20% of the night drivers are drunk. 20% of the night drivers are drunk. A sample of 10 drivers is selected. A sample of 10 drivers is selected. A night driver. A sample of 10 night drivers is selected to study. What is the probability exactly 4 out of 10 night drivers are drunk? What is the probability that 4 or fewer or less than? Okay, what is the probability that 4 or fewer or less than of the 10 night drivers are drunk? 4 or less than, we get at most 4. At most 4. No bigger than 4, no larger than 4. That's why at most only 4, no more than 4. So what if probabilities are at most? Probabilities of at most 4 of the drivers or 10 drivers are drunk. What is the probability that more than 4 out of 10 drivers are drunk? More than 4, we can say that what is the probability that at least 4, or say at least 5, not 4, because it is more than, not equal. So what is probabilities of at least 5 drivers? Okay, 5 drivers are drunk. This is at most 4. This is at least 5, not at 4, because 4 not included. More than 4, 4 is not included. So more than 4, it should be 5, because we don't have 4.5 drivers. That's why more than 4 it should be from 5. That's why at least 5. So second question, what is probability that 4 or fewer, that means at most 4 drivers are drunk? And number 3, what is probability that more than 4 or at least 5 drivers are drunk? Okay, that's why this is not only one. This is only one. Okay, this is we use we use binomial probability distribution. But these two questions we will use cumulative binomial probability distribution. Okay, this is because of one exactly 4. There's only one. That's why no adding. So we can use binomial probability distribution formula. So maybe I am not explaining this. I'm not explaining this again. It's about 8% or 9%. Okay, or you can go to appendix, this page, n equal to 10 pi 20% x equals 4. We can find this one. Okay, the probability that drivers exactly 4 out of 10 drivers are drunk is here. However, you can see this one. Okay, probabilities of a successful given 10, given that 10 trials, and probability success 20 is here. This is a symbol that we use for compute binomial probability distribution. This is probabilities of four success outcome given that or from under condition or from or maybe given that 10 trials probability and probabilities of 10 success outcome 20% or 0.20. We use this chapter 4 formula, slide number 16 on page. Okay, as you go to chapter 4 is about what? Special rules of addition or. Okay, or. So at most 4 drivers are drunk, we add them together with or. At most 4 drivers are drunk, could be no driver drunk, or 1 driver drunk, or 2 driver drunk, or 3 drivers drunk, or 4 driver drunks. That's why we use or, special rules. Okay, special rule. We don't have overlaps. If we don't have overlap between driver, okay, driver A, driver 1, driver 2 cannot be the same person. Okay, driver 1 and driver 2 cannot be the same person. That's why we don't use general rule of addition. We use special rules. Because special rule, driver 1 coming, driver B cannot come in. So the probability that for fever of drivers drunks mean that probabilities are x smaller or equal to 4. So x px of px smaller or equal to 4 equal to p 0 or 1 or 2 or 3 or 4. Okay, that's why this is special rule of addition. P 0 or 1 or 2 or 3 or 4 equal to P0 plus P1 plus P2 plus P3 plus P4. That's why you need to find binomial probability for x equal to 0, for x equal to 1, for x equal to 2, for x equal to 3, and for x equal to 4. But actually x equal to 4 we don't need to calculate, because x equal to 4 we get it from question number 1 already. That's why actually if we don't have question number 1 here, x equal to 4, for question number 2 you need to find x equal to 4. But because it is found from question 1, that's why we find only P0, P1, P2, P3, and then we conclude together because we have P4 from previous question. Okay, so the probabilities at least probability at most 4 of 10 drivers are drunk is about 97% or 0.97. Okay, so the probabilities of driver for fever or less than driver are drunk is about that one, 97% or 96.7. Okay, so when we use a symbol like this one, px less than or equal to 4 under condition or given that n equal to 10, pi equal to 0%. You can see on this page of your textbook. Number 3, probabilities exactly 5. What is probability that 5 or more of 10 drivers are drunk? That's why we call it at least. Okay, at least. That's why probabilities are x bigger than 4, not equal to, bigger than 4. If we know px equal or less than 4, then we can use complement rule. Okay, complement rule of addition in order to find px greater than 4, because when we add them together, equal to 1. Okay, equal to 1. That's why this is we don't need to calculate. We just, if we know that one, we just use complement rule of addition in order to find that one. Okay. Or maybe they don't ask, up to 5. And let's say I say the other example, maybe from 3 or more. That's why probabilities of 3 or more x greater than 3. So h greater than 3 equal to 1 minus ph smaller than what? Smaller than 3. Okay, this is greater than 3. That's why you need to find smaller than 3. That's why take minus 4 out. I'll take a probability of 4. So this one equal to p0 plus p1 plus p2 plus only p3. Okay, this one. So don't need to p4. Okay, so if you got this idea, you can change, or maybe if you find this one, ph greater than that 6. So if we greater than 6, you need to find p0, 1, 2, 3, 4, 5, and 6. Okay, this one should be 6. It is 6. That's why, okay, you can play around this one by your own in order to get more understanding. Okay, so now you go to study your example and your textbook on this page. Practice a review for 6.4 on this page, and exercise again for homework 202, page 203, 204. Sorry, 203, 203, 204. 200, oh sorry, this is 202. 203. Okay, there's no 200. Only 204. 22, 24. Okay. Now the other homework 22, 24. Okay. So 22, 24. So yes, I will stop by this one for now.